Good afternoon. Uh, Good afternoon. Today I'm going to talk about the week 4 lectures, and we will be solving week 4 assignments of the old years NPTEL course on user-centric computing for human-computer interaction. So let me share my slides. Beginning with this week, I think we will start in this week. We are going to go over some of the predictive models. Last week we went over some of the descriptive models. Take a kind of recap of what we did in week 3 problem solving session. So we first learned about this application layer. We saw some blocks components of this application layer. Then we saw the use of this user state predictor. Why is it important? How does it function, and how does it predict the state of a user behavior? Then we saw the differentiations. There were some charts I presented about adaptive, non-adaptive softwares, and then descriptive and predictive models. We learned about 3 descriptive models in detail, and today we are going to talk more in depth about the predictive models. So we had some introduction to it, the GOMS models. GOMS models, there were 4 types of those, and this week we are going to learn one of them. There is also one interesting video of about the CMN model, CMN GOMS model. So I would encourage everyone to go over that video as well. This assignment focused mainly on the KLM model, so that's why I have covered the KLM model in this presentation. So talking beginning with KLM GOMS, so it is keystroke level model, keystroke level models of goals, operators, methods, and system and selection rules. So what does it do is it predicts the task execution time. So given a task a user has to perform, how much time they are going to take while performing this series of operations for performing this task. So for that, to simplify it in a concept map, I've try to make this map. Let me go over it in this view. Yeah, so okay, so this is my CMap tool. I'm now going within it. Yeah, so beginning with this KLM. So this keystroke layer level model is a set of operators. It is a set of operators which are arranged in sequences. Okay, I think this is very distracting. Yeah, we'll go over this only. Okay. So a KLM model is a set of operators arranged in sequences. So we get the operators, and then there will be sequences about them. What are these operators? So the operators is what lets a state go from one level to another. It has what is an operator? It represents a cognitive activity or a mental thought process of low level. So this is a mental action of the user at a low level. And the operator also represents cognitive activity with time, which is predetermined and is fixed. So, I'm sorry. Let me begin once from the top. KLM model is a set of operators arranged in sequences. So these operators, what are these operators? These operators let a state go from one level to another. So how does the user state change? That answer is with the operators. The operators represent the cognitive activity of low level. Simply thinking about making a decision to click save. That is a kind of cognitive activity. Or making a decision to go from this point to another on screen. That is also a cognitive activity. Making a decision or something like selecting among different choices, that is called as an example of cognitive activity. It is a cognitive activity of low level, each operator is. And this cognitive activity is also measured, defined in terms of the time which is predetermined. So it's not like it's a big activity like thinking about what to make in on the screen or what to draw on the screen. So that can't be a measurable predefined fixed time activity, right? Even though it is cognitive in nature. So what we say is, oh, so what we are saying is, it is a cognitive activity which is measurable in nature, and it is predetermined. It has some fixed time, something like thinking about going from the one point on screen to another, making a decision to click on something or choose the something from the menu. Like over here you see that in the Google slides there is so many options in the menu. But if my intention is to open a file, I will have to make this decision that I want to click on file first, and then I want to click on new, then presentation. So these decisions that I'm making is representing a small scale cognitive activity that is time bound via predetermined and fixed time, which becomes the operator for that particular action. Now, these operators there are seven types of operators. Okay, seven operators in total, divided in three types. So, five of them are physical motor type, then one of them is mental type, and then there is a system response operator. So, now let's first go into the question about operators, and then we will go to these different seven types, seven operators. Okay, so let's go and we'll be back to this diagram again. So there's this old assignment question about the keystroke level model. The primary objective of keystroke level model is to allow a designer predict the satisfaction a user will get after performing an interaction task. Is it true or is it false? So the keystroke level model is not used to predict the person's user's satisfaction. It is supposed to predict the user's um, at action time or task execution time. So how much time will they take if a task is designed in this way, if the layout is designed in such a way, how much task is supposed to be is the user going to take. So the answer is false. Now talking about these operators, so I told you there are seven. Out of these, first five are physical motor. So that is kind of representative of the motion that we perform over the screen. So this model is from early, I think, 80s. So that's why it's pretty it has some motions which are not now required in the devices of today, in the modern era of computing. So we'll still see them. K represents the operator task of key press. So if you are pressing any key on the keyboard, it is called as K. A mouse button press release is represented by B operator. So if you point clicking your mouse to click on any button or and then releasing it, it is called as B. So click kind of thing is represented by B. Now the pointing task, that is moving one pointer from one to another place like this, or maybe we can say in this like this, it is represented by P. The homing task, so when you are switching your operation from the touchpad to the keyboard, maybe you are using some mouse or other device, maybe you are drawing something using a stylus. So all these actions require going from one device or one physical platform to another. That is known as homing. So if I switch between the keyboard and the touchpad, that will be called as the homing time. Then D is drawing a line using mouse. So now we don't use drawing a line action. Pretty much nowhere we need to use it. Then there is mental operator called as M. It is the thinking or decision making task. Remember, all of these are actions that are performed within a particular predefined time. And the R is system response time. So that is a kind of system response operator that gives us the time in which the system is supposed to respond to the user. So if you see over here, when I perform the action of a click by a keyboard, I perform the action of key press on the keyboard, I see that the last line appears. So this appearance of the last line takes a very tiny bit of time, and that is known as the system response time. Now let's look at what are the different timings that has been recorded for each of these actions. So for the key press action on the keyboard, the execution time for a kind of good typist who has very uh, has been using keyboard quite a long time, it's just 0.12 seconds, so it's not even a second. And then for a poor typist it is 0.28 seconds. For a non-typist it could be 1.2 seconds. So it would take some time for the non-typist to find out the keys, and that's why it takes about a second for them. Next one, for the B, that is the button press or click option, you require 0.1 second. For pointing option, that is moving one pointer from one place to another on the screen, you need about 1 second time, 1.1 1.10 seconds. And then for the homing task, that is switching between different mouse pointer or the keyboard and touchpad, all this switching, it requires less than a second. Now this, since this drawing a line is not used much, and then system response times, we also know last one, that now that technology is advanced, devices are so fast and operating at a very low speed, nanosecond and millisecond speed. So that's why system response time is very high. So we don't worry about this time and this drawing a line time. We will talk about this mental thinking task time, and that is popularly known to be empirically found out, that empirically found out as in many experiments were conducted, and same tasks are supposed to be performed by a certain number of individuals, like in thousands, and within those thousands of individuals it was found that it takes about, on an average, it takes about 1.35 seconds for a normal person to make a decision, a normal user to take a decision. While I say normal user or normal person, what I mean by that is an expert who has already used a system. So it could be an expert who has used the computer or used the mobile interface on which you are designing. So that much time is taken by an expert user for making a mental decision, that is, I want to do this now, that decision. So I think from these timings we can see that the highest time is taken for the non-typist to type, or for pointing from one place to another, going over the screen, so traversing the screen from one place to another desirable location, or making a decision. So these are the three key points where the user is spending a lot of time. Now So this is another old assignment question. So the KLM operator K, the operator represents the task of any key press, falls under which group? Is it physical motor, is it mental, or is it a system response? So when I key press, I have I am do what I'm doing is so when I press the key, what I'm doing is I'm performing a physical motor action with my hand, with my fingers. So that's why it is a physical motor action. The operator M in LKLM falls under dash operator group. So that falls under M in the operator. What was it? The mental decision making. So decision making falls under this mental category. So it is important that you know all these different operators for exam preparation as well as your assignment writing. It may not be important to recite all these timings, but it is good to know that which actions kind of going to take maximum time for any user, right? Now, mm, now let's go towards the this part. Let's go back to this concept map now. Why do we know all these execution time? What is the execution time and all that? Because to make a model which is KLM, it has the analysis steps. So in these analysis steps, what we do is we choose a frequent task that the user has to do, has to perform to in the application that we are doing or in the software that we are doing, and we have to build a KLM model of for that task, for that frequent task that the user has to do to perform a certain action. How this is done? The KLM model is done by identifying the operators that will be involved. These list of operators, now remember this list of operator is there. We have to identify which one to take out of these, which ones are applicable for this specific action or specific task. So we have to list them down and we have to arrange them in sequences. So which action I will perform after which one, which operator should be used after which one. That is the step by step manner in which we decide what will be the operator sequence, and then we build the KLM model. Now why do we build the KLM model? Because we that the total of the KLM model, each total for each identified operators and taken in this sequence gives us the execution time. So that's how we find out what is the task execution time. So to find that out, we need to model this. So now I think we can go towards the next one. We will see an example also in this 5 rules of thumb for M operator placement. Now, before we go over here, let's take an example. Okay, I will give this example, or we will take this example later. What I will do is I will explain now here only. Say I want to just what I want to do is I want to see the file click over here. I want to open this file menu and I want to download this presentation. Okay, so I go over here, I go over the option. So what are the actions, cognitive actions that I'm doing? What are the operators? How to identify them? So first we think about what are the actions. This is a frequent task that I'm going to do. So here KLM model having a KLM model would be very useful. So what I will do is I will write down the steps. First I have to decide to open the file menu. So I click a press. I press a key or press a touchpad, mouse pointer. I press it. So this is a button. B action. So first I decided that I want to open the file menu. There was an M action where I thought. Then I click the mouse pointer. So this is a button action. B. Then I have multiple options over here, right? Out of this I have to choose which one I want to do. So I want to save it, so I want to download it, so I make a choice, right? That is a mental action. So again then I in the here I don't have to press a button. I just have to move the pointer from file to this download side. So that is a P action where I'm moving the pointer. Next I am going into this menu. I am again doing the pointer actions because my pointer is moving, P action. Then I'm also, while doing this P action, I'm also thinking, right? I'm reading what is written, what is this option, and with this option, each option I'm thinking. So now I will choose this PDF document maybe, and then I have to select something and then save it. So this entire up to the saving block arrives, I have performed a set of different operators. Like I began with M, then I clicked so B, then choice, so then M again, then pointer moves, then P, so then again the pointer moves, so MP, MP for each action. So these are the way in which we model the sequences. And for each MP we saw that over here we have seen that if I am performing M, then I am going to consume this much time at least. If I am going to perform P, I am going to consume at least this much time. For B, I am consuming this much time. So depending upon what is the set of actions to be followed, you can again do the calculation that you can just add up all the times to find what is the total time taken from clicking the file to the saving option, till the saving window pops up. So that gives me the task execution time. So that's an example. Now we will go towards these 5 rules of when to put the M operator, because we might argue that yeah, thinking to we are already doing, thinking is not happening something externally. So there, but then where to put the operator, right? That is the question. So for this rule, for this question, we have 5 rules. Rule number 0 is talking about when you are giving a command and when you are adding a argument. So command is when you are actually clicking buttons or checkboxes, radio buttons. You're actually performing the task of key press or mouse clicks. That mouse click, before you do that, you have some thought process which gives your motor organs that command that you are supposed to perform this now. So that is the command type. And then there is argument, that is text entry. Hello Raju. Yes, we are going over the 5 rules of thumb for the M operator placement. So
Yes, yes.
yeah,
Actually, sorry, I joined late. I was in office only.
no problem, no problem. We will continue. So if you want me to go over the previous slides, there were
Yes.
1 or 2 assignment questions that we covered. You want me to go over them once? You can quickly.
Go on. Maybe I'll. Yes.
Okay, okay. So these are the different operators that we will be going through. Basically, these are the steps whichever we perform while we are performing any task over a screen. So for example, K represents a key press, or B represents a button press, like a click, mouse click. Then P will
Right.
represent a pointing task. Am I audible?
Yes, yes.
Yeah. Then H represents homing task, that is switching between different platforms. Like I am using keyboard for some time, then I'm using some touchpad, or I'm using a mouse. So switching between these platforms is known as homing. D is drawing a line. So nowadays we don't need the systems that have drawing a line as an action. So this is not really observed now. Then very important part is this mental actions. So whenever we are performing small cognitive actions like making decision, it is shown as known by M. So why are these codes there? So that these codes are there so that, say you are mapping out a sequence of actions for performing a very simple task that is frequently happening in the design that you are making. Okay, so in a software that you are making, a very frequent task could be opening a new file, or saving some file. So if you go into a deeper granularity of the each and every task, you will find there are so many steps. Like, you have to look at the menu, choose the file option, then within the file option there will be multiple choices to select from. You scroll towards the option that you are intending to do. Like, for example, if you find file, there will be new, open, then there will be save. So say you have to save, you have to take your pointer there and then click on save. So when we go towards this finer level of granularity, and we inspect what is the action that we want to perform, or the sequences of action that we want to perform, describing everything is a time taking process. So instead, this KLM model, we describe this using these codes. So suppose I am performing the action of key press after taking my pointer somewhere, then it would be represented as PK. So I first took pointer somewhere and I did the clicking, click the say enter. Or maybe I clicked a button. To click a button, I'm taking the pointer somewhere, so PB, that would be the action sequence. So usually what in KLM model, what they do is, frequent task, whichever it is, about within the system, that is going to happen multiple times, they model this KLM, this task based on KLM model, so that you get to know this how much time does the average user take to perform this frequent task. So that gives an idea. If the frequent task is taking too long for the users, then they might get bored while using your software, right? So you want to reduce this task execution time for them. That's why this whole entire exercise is done. First, you map the process of performing the frequent action using these codes, and then you calculate the total time of execution by adding up the entire process's times. So these are the times that we know that a user takes. Out of these are the few, like this one. For a non-typist, key press is a time consuming task, or for a regular person, pointing I mean, traversing a pointer, moving a pointer to a target, that takes a longer time. Or thinking, making a decision whether I want to save, or whether I want to move ahead, or move a file, or whether I want to copy a file, which one to click, what when to press a key. All those mental decisions, that takes about 1.5 second. So that is also time consuming. When you add a lot of these sequences, you will see that the overall output is in some seconds. So even that is really time consuming, even though it is a frequently happening task. So to reduce the entire execution time of the task, we are mapping this and using the KLM model. So the old assignment question was, the key press falls under which operator group? So out of these first are the physical motor operator groups. This middle one is the mental operator group, and the last one is the system response time. So it is system response operator group. So do you have a guess of which one key press would be? You can write your answer in the chat box, or you can say also. So basically, the key press action is done physically using your hands. So that's why it will fall under the physical motor type. The next question is the operator name M. Yeah, right, correct. A is the correct answer. And for the next one, operator name M in KLM falls under dash group, dash operator group. The first one was physical motor, the second one was mental, and the third one was system response.
B, I guess.
Yeah, yeah. B is
Yes.
correct. Very good. So these were actually the old years assignment questions which you may expect in the next coming exam also. Now we'll
Right.
go over the 5 rules of thumb for M operator. So because this M operator is about decision making or thinking, there might be some confusion how much and when do we think, right? So that's why they have given some rules for when to put this M operator. So there were two actions. One is my mouse is operating widgets like buttons or checkboxes, radio buttons. So the key action is happening. So at that time, some command is there, and otherwise there is keyboard keys pressed. So text entry is taken. So the K and the this is the K action, and this is the B action. So before any K and B action, we have to kind of add the M. So insert M in front of all the key press operators and the pointing actions done for command selection. However, do not place M for the P that is used to place the argument. So if you are giving the text entry somewhere in the text box, you are writing something, you might see that there are multiple K pressed. You don't have to give an M argument before M operator for before that key press thing. When we are going to do the key press thing, M before key press, it is only when key press is done to give a command. To give you an example, if I were to write my somebody's name on this slide, say I am writing this example. Okay, when I wrote this example word, I am pressing some keys. But if I am going from this slide, I selected slideshow, and then I'm clicking on the arrow keys for so that this action is happening. So when I'm doing the arrow key press for moving this slides, I'm performing this command action. I'm performing this command action. Even though I'm pressing keys, I'm performing command action. But when I'm entering a text, as I wrote example letter, I was still using the keyboard, but that is for the argument text entry. Okay, that is the difference between the key press of command and key press of argument. So the rule states that if it is an argument, then don't write M. You don't need to. There is no decision making that you are performing while you are typing text. Whereas if it was key press to make a decision, like saying enter or sometimes control S, so these are two keys that I pressed, so that is indicating of a decision of saving. So then in that case, key press will also have M operator before that. So when I'm saying I pressed control S to save a file, what I am doing is I'm pressing what is the operator sequence that we are performing. First I will say M because it is key press for decision making, then M, and then I am pressing two keys, right? I am pressing the control key and I am pressing the S key. So there is this action sequence is MKK for this action of saving a file with control S. So that's how we say this rule 0, that you will add M before any command action. So here is an activity. You have to follow this rule that whenever you are entering text, you don't need to have M before that. But when you are clicking on something and then clicking on something, or you are doing the key press for decision making, or you are clicking on a button, then in that case you have to add m. So can you guess what would be the operator sequence for this? If I were to fill this k, I can click over here, say Kate, over here. What will be the action operator sequence? So the operator sequence would be, first I will click on this text box, first text box. So I will have a clicking action, that is button press B. Then I will enter the text. So before this button press B, I have to add the M. I have to add the M. MB. Then I am typing text. So there is KKKK. That is for the 4 letters of Kate. Then next I go to the pointer action. That is, I'm taking my pointer from this block to this block. So that will have the action of P. So for P, before P, I have to think that I have to now move from this block to this block. So MP. Here we are in this block now. So what I'll do is I'll write also here. Yeah. So we'll start writing. We started with this, clicking over here. So we started with M. Then we typed this 4 letters. So I will write K, 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 K. I right before typing K, I clicked on the this right this box first. Then after this Kate is done, I have to go from here to here. I take my pointer over here, and to perform this pointer, I take the MP. Then within this MP, next I have 3 letters to write, so I will write K, K, K. Then going from here to here again, I am doing the MP action. Then clicking on P, submit, I will do the MB action. So now the action sequence that we are performing is MBKKKK for Kate, and then moving MP, then again typing the next one. Oh, before typing here, we did the MB. Before typing, I have to click over here, right? So that is again button press. So this MB there, and then KKKK, then MPMB. So there is 2 sequences of MPMB that took place. Okay. Remember, this is our answer. We will come back to this slide again. Okay. Next. So continuing the 5 rules of thumbs for this M operator, we found out what is our answer for this one. Sometimes actions like this BK are expected, so we can't say that before. Okay, here actually we should have written BMK, and here again we should have written KK. Before K we should have written an M, because what I have to type, I have to start typing. Okay, so this rule actually states the same thing, that sometimes the actions like BK are expected. For example, now I have clicked on this, then I will start typing. That is expected. So even though there is place to have another M before the K, I should avoid it. So the rule number 1 is, if an operator following an M is fully anticipated, you are already expecting that is the only thing that you can do. So that is why you clicked B. So that's why an operator is immediately preceding that M, then M should be deleted. So that takeaway forces me to take away this one. So these M are going away. We'll not cut them, we will do this. Yeah. So this M that already I know that I have clicked because I want to type next. So that's why I remove this M. Similarly over here I am clicking that's next because I want to type next, so I will remove it here. So here I have applied the first rule. Okay, so that is the first rule. Next we will go to the second rule. What if you have to type a word consisting of multiple KKKK operators? So you don't need to write M for all the units. Combine all the M's for the same unit value. Or now here you might think that it is related to text. So that's why we didn't use the M over here, right? Because we are entering Kate and Do. These are arguments. We are not giving commands over here. But in some cases commands are given. For example, I'm doing the control and paste action. So sorry, I'm going doing the copy and paste action multiple times, copy paste through command line interface. So in the command line interface, when I have to type, it is the KKK operation. Again, you remember the command. I hope that you guys who are listening know the command line operations. In your Windows PC, if you go to the run and then you type some command to run, so that is the command line application. When you have to type a word within it consisting of multiple key presses, you don't need to add every time you press a key. You don't need to add an M before that. So if a string of M's belong to the same cognitive unit, remove all the M's except the first. So while here I will say, are there any such cases? So we can see that P and B are two different cognitive activities. Sorry, physical motor activities. Similarly, this P and over here also P and B are similar activities. So we do need to preserve these M. We cannot delete these M's. But otherwise, if the cognitive activity were to be the same or similar, you don't need to uh, put an M before each of it. So to give you an example of it, sometimes when we are doing something, we have to click on multiple times next, right? So this next we are doing might be using an arrow key, might be using a touchpad. Every time are you doing the thinking again and again, decision making time again and again? Sometimes no. So this entire process of clicking on all the series of next, that can be combined and represented as one M before the first clicking activity. That's the takeaway for this rule number 2. So rule number 2 talks about this cognitive unit. Cognitive unit is multiple times you are performing the same action, similar action again and again. So you are not putting a lot of thought in each time you are clicking or pressing a key. So that's why M can be written as a representative initially only. The rest you can avoid. Then the third rule now. Initially we saw that similar to rule 1 for the carriage return actions. So we have carriage return. We know we similarly to that we don't place an M before consecutive terminators. So what is the carriage return? It was the rule 1. Rule 1 was that next what will you do is fully anticipated. So this B and K, here we click on we perform this click operation because it is kind of an enter, so we don't need to give an M before that. Similarly, while the ending part also we don't need to give the M for those places. uh, for the carriage return, as in when you click on the enter or when you click on the submit, so that is supposed to happen, right? You are entering the text and then you're clicking submit. So you're not actually making any mental process while clicking on submit. So that's why from here I will delete the M, because otherwise For example, over here also, so first I did this and then I moved my pointer to this location, the other location. Here it is required because where to go, that decision I have to make. But once I have done the previous entering part, I may not need to again think about clicking over here. So here we can remove that. So now applying the third rule for carriage return action. Carriage return action means ending of the entire text addition or something like that, command addition. At the end, you don't need to give if the delimiters are similar, then you don't need to add m before consecutive terminators. Now the rule number 4. Yeah, so we spoke about this example of command line and we spoke about typing copy paste over there. So if you are giving a delimiter key every time, key press, for example enter, pressing enter after each, so the key press represents the delimiter that follows a constant string. The same string is being repeated multiple times, then in that case you don't need to put an m in front of it. But if you are doing a variable string, for example first you write copy, then there is the next command you are giving paste, then you need to preserve the m's, you can't delete them. Basically performing the same actions using command, that is going to be if you are performing the same action using command, the decision making is not really required at each instance. So then m at the one beginning is also enough, you don't need multiple m's. And second part, then if performing different action, then there will be some decision making to change the action, right, to change the command. That's why m we preserve over there. These are the 5 rules of thumb for M operator placement. So let's revisit the R for newly found. This is the final, in which there is no overload of this mental action. So while adding this simply writing first and last name do over here and clicking on submit, you see that this is the kind of long sequence of command that we do, sequence of operators that takes place. And then KLM, how is it calculated? You have the execution time for each of these steps, then you go on adding all, combining all of them, and you get the entire task execution time. Probably it will be around like 1 or 2 seconds for a person to write their own name, or 3 seconds. I don't know. There are two m operators, so there will be two to three of m operators, so there will be 3 into 1.35, so it will be higher than 2 definitely. So you see that it takes a little longer, 3 or 4 seconds, to perform the entire action of frequent task of entering your first and last name. So we are done with the 5 rules of thumb of M operator, KLM. So up to now, what all we have done, we went through the what is a KLM operator, a KLM model, what are operators, what are the sequences, what are how to calculate the total execution time of KLM operator, what are the 3 different types of operator within the KLM operator, that is physical motor, then mental, and then system response. These 3 types were there. And we then saw that KLM model can give us the total task execution time, and there are some rules of when to apply the M operator placement. So that's it about the KLM model till now. Now we will go to the Fitts law. What does Fitts law predict? It is another predictive model. So it predicts the task difficulty in human motor performance, that is target acquisition task. So it is to do something to do with moving or finding an object and moving it, acquiring an object. So target acquisition task is what we are going to evaluate the task difficulty in a target acquisition task, with the Fitts law. So it was invented in 1954 uh, by the human motor system, about the human motor system, where actually an object is placed in an environment of the user, and the user has to go to that object and pick it up. So there is time consumed based on there is difficulty based on the distance at which the object is placed and the object's width itself. So if it is a tiny object, it is difficult to to locate it, and then difficult to pick it up. But if it is a bigger object, it is easier to pick it up. So that's the kind of way in which we say that task is difficult based on how far it is and how much width of the object is. This law assumes that the task is rapid, aimed, and error free. So, this is very important. These assumptions are very important because it is not for a slowly happening task. So, that's the rapid. It is aimed. So, there is a goal behind this task, and it is error free. So, the user, whoever is using it, doesn't make any mistakes while choosing this object. That is the highly important assumption of this Fitts law. How do they model this task difficulty is with the use of an index of difficulty. I'm just going to take a sip of water in a minute. Thank you for waiting. So, this index of difficulty, it is represented as a mathematical function of two quantities. That is, we already talked about this in the previous slide. That is the distance and the width of the object. So, distance at which the object is placed and the width of the object. So, you can see that width is in the denominator and distance is in the numerator. So, the task difficulty or the index of difficulty will be higher if the object is at a far away location, and if it is nearer, the index of difficulty will be lower. So it is proportionate, whereas this is not actually proportionate. It's a log relation. But then if the width of the object, so if the object is very small, tiny, it is very difficult to acquire it. Whereas if the object is good enough, of a broad enough width and height, then it is easier to acquire it. That's the basic sorry that's the basic behind the Fitts law of task difficulty. So there was this old assignment question. Fitts law is a model of human vision performance, human vestibular performance, human motor performance, and human auditory performance. So we know that the answer is human auditory performance. Oh, sorry, human motor performance. I made a slip. Yeah, so human motor performance. Next, we go to the another question. Fitts proposed a measure of task difficulty called as. We just saw the equation. It is the index of difficulty. So now with Fitts law, what do we calculate? We calculate the task execution time. We call this task execution time as throughput. So throughput is a function of this ID, that is the index of difficulty, and the time that is taken to perform the entire task. So it is to identify. How do we do that? How do we find out what is the throughput? The first step is to identify a set of participants and tasks. Each participant is, so it is a large number of participants, okay, and what task they will perform, that also we have to find out. Each participant is given the same set of tasks that is preferable. Then step number 2, what we'll do is we will determine the throughput for each person, and then compute the average throughput, and we will call it as average throughput. Okay, so average of all the people's, how they perform this task, and there will be some equation of ID and task time, MT. So we will have a kind of, yeah, I know the equation actually. ID upon MT. So ID has units in bits and MT is units in second. So our throughput is ID per second. Okay, so so we will calculate the average ID upon MT for each of the individual person. So for every, remember, for everyone the MT is going to be different and the ID is going to be different for each person. So that's why we have to calculate the average of the throughput, and we will call this as average TP. Then we determine the average task throughput for all the tasks. So first we did give the same task to everybody. Then we give another task to everybody, and then give another task to everybody. And now we have the set of tasks and we have the set of average throughputs. Then we take the average of all the average task throughputs. This is the throughput for the test condition. Okay, that's a kind of study we do for finding out what is the throughput using Fitts law. So here they mention that speed and accuracy is always a trade-off in Fitts law, because if you want to do something faster, there is a chance that error may happen. So you remember that Fitts law was brought up on this assumption that error is not going to happen. The user is going to perform a task without error successfully. But in reality, for people don't work that way. People will make some mistake. So that's mistake can be there is a trade-off between whether you want them to perform things faster or whether you want to perform them want them to perform things without error. That is called as a speed accuracy trade-off. So the target acquisition accuracy, it increases if we perform the task slowly. We will perform, there is a chance that there will be error free execution. Wherever However, accuracy decreases if you want to do this faster. Similarly, if the task is in the smaller size, the task that we want to perform, say it is represented through a smaller size, very tiny smaller size, the person to execute with, then it is kind of prone to error. However, if it is of the size that the user is accustomed to usually, then it is kind of predictable that the user will perform it correctly because they are acquainted with the size. So that's the trade-off about the size also, and we will discuss this more in the next slide. Error assumption in the Fitts law. Say within the 20 attempts that a person performed the same task, if they are performing it erroneously for 4% of time or below 4% of time, we can ignore that they have made an error. We can say that there was no error, they can perform with this efficiency. Now if the error rate increases by above 4% in terms of the attempts that they are doing, if they have made errors in the 4% or more times, then we have to consider about the make considerations about the effective target width. So target is the object that we are trying to hit or we are trying to locate, and that target's width is the thing that is making the error possible or error more prone. That's why to reduce this error, what do we do is we broaden the target's width so that the area of where the person can hit correctly, it increases. So this larger area gives us the hits plus misses that were previously happening also fall in the correct zone. So the error rate gets reduced if you are covering a larger area of an object. That was the trade off, the discussion ahead of the trade off. We have one question in the old assignment about it. While acquiring a target task difficulty, dash with increase in target width, whether it will increase or whether it will decrease. So the task difficulty will sorry the task difficulty will decrease as with the increase in target width. That's why we know that if something is not properly going away from us because it is a lower font size, what we generally do, we increase the font size so that we avoid making error over there. That's a kind of an example. Okay, moving ahead. The last law that we will talk about today is Hick-Hammond's law. Initially, if I give you a recap, we talked about the KLM model. The KLM model was keystroke level model. Talks about the physical, motor, mental, and system actions that we perform, and is used to calculate the total execution time. The second law that we saw was Fitt's law. It talks about the what does it talk about? The task difficulty. So it is a metric of task difficulty in terms of index of difficulty. And using this index of difficulty, we calculate the throughput of a task for a particular user. So this is the recap. Now we begin with Hick-Hammond's law. So uh, it is for calculating the choice reaction time. The law models a time person takes to react in presence of a stimulus that presents a lot of choices to the person. So if given a lot of choices, how much time will I take to make the choice that I want to make, that and react on it? That is the choice reaction time. So it is also represented by RT. The law states that reaction time, this RT, increases with the increase in uncertainty about the judgment or decision to be made. So basically, the number of options that there are, higher the number of options that there are, or greater the number of options that there are, I have to make a informed choice multiple number of times. So then my reaction time is obviously going to increase. Another reason why this reaction time would increase is if two options presented in front of me are too similar, then also this reaction time might increase. So while solving question papers, you might be facing this dilemma sometimes that two of the options I think are correct, but I don't know which one is correct, right? So at that time, you face this choice reaction dilemma, or choice reaction is the problem that you are facing, and the time that you take to solve that problem, that is the reaction time or the choice reaction time. Okay, choosing when presented with multiple choices, choosing the option to react uh, by making a choice, that is called as choice reaction time. It increases if the uncertainty increases. That is the basic law. But to measure this uncertainty, what do they call? We call it as entropy, or H. So previously in thermodynamics or chemistry, you must have heard about entropy. That is basically the overall systems uncertainty, or the kind of process that goes on in the terms of uncertainty or equilibrium, right? So that is the measure of uncertainty. For the scope of this law, we take the measure of uncertainty when presented with multiple options as the entropy. So we also now know that reaction time is proportional to that entropy. The entropy is number of choices, number of the extent of uncertainty. So if extent of uncertainty it is higher, then reaction time is going to be higher, because that to process that much, that will take longer time, right? So the proportionality, it is basically given by this proportionality regular function RT, reaction time, is equal to some constant A plus B, that is some constant B into the entropy. So how do they find this A plus B? They kind of find it through multiple number of trials. So H is calculable, and it can be calculated using the probability of making the ith choice. Say there are 5 choices for me in the file menu, and I have to select the new file option. Then this making this choice to click on new, that is the ith element, right? First, second, third, ith element. So this is the sum of the all the options, the choice making probability of all the options, which is the uncertainty. So if there are n elements which are which can be chosen equally, I mean the choice probability doesn't differ, then for those n elements the reaction time can be given simply by this function a plus b into log n raised to 2. So that is the way in which that is the depending upon this number n, that is the number of choices you provide, this is going to increase, the reaction time is going to increase or decrease. So multiple number of choices, multiple number of the reaction time will increase. Lower the number of choices, then the reaction time will lower. Now assuming that the choices are clear, otherwise the reader might get confused, no, what is it meant, is it similar, so that will also again take time. So assuming that choices are clear and have equal probability, this is the time taken for each, and this a and b are found by repetitive trials. You identify a set of participants first, make them perform the task, vary the task by varying the number of choices. So in the number of choices, you first give one choice, two choice, three choices. Like that you go on varying the number of choices. Determine the entropy for each task. So every time you have the number of choices different, you have the entropy for the less or more sorry, the gradually increasing uncertainty, you have the entropy. Then empirically determine the reaction time for each task. So you can empirically by experiment determine the reaction time for each task, maybe using some stopwatch or system recording timing system logs for each participant, and take advantage of all the take an average of all the participants. So what did the all the participants do, what was the reaction time for each um, increasing entropy task for each participant. So you will get a list of average of all the participants performing the number when performing the same task, their reaction time to perform the task with least entropy to the task with highest entropy. Then you get a RT, that is reaction time average for all the participant, and H for each task. Plot these values in an RT and H plot. RT will be alongside the y-axis, H will be along the x-axis. Now you use the linear regression on the data points to relate the RT and H with a line equation. So you might be now while reading this, it may seem like it is a big difficult task, but there are now tools that will give you the linear regression fit, and then they will also predict the values of a and b for you. So once you get the a and b values, it will now be possible for you to determine कि say first we have taken the choices, only one choice, what was the entropies we calculated, we found out the reaction time, we found out the average reaction time. Then for the two choices, what was the entropy we calculated the reaction time for two choices, and then we calculated the average reaction time. All these things we did, then we plotted them, and then we fit it across the RTH graph, and then the fitting curve will give you the a values of a and b. Now you can predict for, even though you have not performed anything or you have not made anything for 7 choices yet, you will get to know the estimation that for say one choice, if it gives this much reaction time, for two choices it gave this much reaction time. So for how much of entropy, that is for 7, whatever will be the entropy for that level, what will be the reaction time, that can be predicted. So that is predicted by the fitting model. So that is the Hick-Hammond's law. There are, I think, one or two questions about the Hickman's law. The dash models the time a person takes to react to a stimulus in the presence of choice. Of course, since we are learning it here, it is based on the Hickman's law. And the measure of uncertainty that is used in Hickman law is called, it's not efficiency, it is not effectiveness or unity, it is entropy. So here we have reached the week 4 ending. I'm glad that today we had some participant interaction with Raju who had joined. I encourage all of you to be a part of this interactive session so that we can have a conversation. I can solve the difficulties that you face. Basically, my intention is, if you are going through the lectures or the transcripts and video lectures, it might be too overwhelming for you, coming from maybe Hindi speaking, maybe non English speaking backgrounds. So that's why I'm here, to help you out and solve these problems for you. And also, uh, these while we solve these problems from old assignment, we are also kind of opening up a pool of questions that you might expect for the exams. One more interesting thing is, if you have gone through the assignment with me, the old assignment with me, and gone through these slides that I presented, what I have done while preparing these slides is that I tried to have all the current assignment questions answers as well included within the slides. So when you go over the material that I present every time, you will get to answer this year's current week 4 assignment with very much ease. So even if you didn't join today's session, if you're watching it later on, and also on YouTube maybe, or you have access to the slides that I've prepared, then please do submit the assignment, because to complete a NPTEL and get a certificate, you need to have 25% score of your assignment score will be considered, and it has to be kind of good, so that you get a good grade. And then if you get a good grade, then only you get a certificate. All those requirements are there. So I am hoping that through this interaction you at least get to solve the assignments on time. Try to solve them and submit them, because you can submit as many times as you want. You will get multiple chances till the deadline. So at least try and attempt them once after watching this video. Thank you for watching this video. I have added it to the playlist, so you will be able to follow up with the previous week's assignment as well. And we will upload the next week assignment. I'm hoping for some interaction, because I've kept a lot of activity slides. When you're watching NPTEL videos, you may not be having any face-to-face instructor time. Here you have the opportunity, and we also solve problems like an interactive activity here. So that will be something that you might be missing. So if it is so, please join the next class. We will meet on the next Tuesday, 7 p.m. Thank you.